Great to be here. Thank you, organizers, for such a nice workshop and for the invitation. I'd like to talk about this topic of approximate optimization with quantum annealing. Quantum annealing, I believe, fits squarely into the theme of the beyond gate model, or maybe in some sense parallel to the gate model type of approaches to quantum computing. And this is work that was done primarily with Humberto Munoz-Bauza, who's a former graduate student and now a postdoc at NASA. There's also a bunch of, in the small print here, many earlier papers that this work is based on as well. So let me dive right in. The topic is approximate optimization. But let's start with exact optimization, which has been the driving force for quantum annealing and adiabatic quantum computing for the past 25 years or so. So the problem is to find an exact optimization, to find the exact one or more, if there's degeneracy, ground states of a classical Ising model, where you assume that you can program the local fields, the H's, and the couplings, the J's. So what I'd like to talk about is whether we can solve this kind of a problem with a scaling advantage over state-of-the-art classical methods. Or perhaps we need to change the paradigm from exact optimization to something else in order to achieve this goal of a scaling advantage over classical computing. Okay, so to give a more formal statement of what quantum annealing, or sometimes adiabatic quantum computing, depending on where you put the starting point, it's the following, right? So we prepare some n-qubit system in the ground state of a transverse field, which gives you a uniform superposition state. And then you start evolving adiabatically according to this transverse field Ising model, Hamiltonian, which we already heard about a couple times today, with annealing schedules. So the function A turns off the transverse field, and the function B turns on the Hamiltonian of interest, the Ising Hamiltonian. And then at the final time, TF, you make a measurement in the computational basis. And what we know is that, according to the adiabatic theorem, if this evolution time, TF, or the anneal time, as I'll often call it, is long enough compared to the inverse gap, or inverse gap squared, or sometimes inverse gap cubed, depending on which version of the adiabatic theorem you employ. So if this annealing time is large enough, then you're guaranteed that the system will be close to the instantaneous ground state at the final time. And if you're looking for the ground state, well, then that gives you a guarantee that you can always find the solution to the optimization problem. But of course, the problem is that this time can be very large. In fact, it can scale exponentially. If the gap scales inverse exponentially, then your time will scale exponentially. So in practice, that's not exactly what you do. You don't try to satisfy the conditions of the adiabatic theorem. Besides, it's also hard to find the gap. So yeah, you'd have a hard time trying to even estimate what this time is. So in practice, what is done is you pick a final time, or an anneal time. You run the anneal, and you measure. And then you expect to get the correct answer with some probability, P, or I'll call it P of ground state, which depends on the time TF. On the anneal time TF. So that leads us to needing a metric that is going to help us quantify performance. The time to solution metric is the conventional approach here. And this metric is useful not just for adiabatic quantum computing or quantum annealing. It's useful for any probabilistic algorithm, in particular any probabilistic quantum algorithm. So let's say that we want to find the correct answer at least once with some desired probability, P sub d, which let's say is 99%. All right, so you want to make sure that you find the answer with that probability at least once after some number of runs. So what will you do? Well, you set the probability PD, the desired probability, the probability of at least one success, equal to, what is it? It is 1 minus the probability of 0 successes after k runs, right? And the probability of 0 successes, that's 1 minus the probability of a success to the power k after k runs, assuming that the runs are independent. And so if you now solve this equation for k is the number of runs, we can back out from here the time to solution. The time to solution is just the actual time it takes to run the process times the number of attempts that guarantee that you will succeed with probability p sub d after k runs. Okay, so plugging in this k, you get this formula, which for small success probability is actually simply the total runtime divided by the success probability. And that makes intuitive sense. All right, so if your success probability is very small, you expect your time to solution to be very large, and vice versa. Now, there's an important caveat here, which is that we need to optimize the runtime in order to minimize the time to solution. Okay, so I'll come back to that in a second. So it's very, very important that we optimize the runtime to minimize the time to solution. Otherwise, we're going to get fake scaling results, which you'll see in a second. So now, with this time to solution metric, we can define what we mean by quantum speedup, and it's what you'd expect, right? So I'll say that I have a quantum speedup if the optimized time to solution scales better with the problem size than the best classical algorithm. And the best classical algorithm, of course, is something that you may not know. In many cases, we don't have heuristics. In some cases, we know what the best is. But in most cases of interest, we're going to have to settle for heuristics. So then we're trying to beat the best available or known heuristic. Okay, so now back to this point about needing to optimize the runtime. So here's an example of what happens if you don't. Here is the time to solution. So again, think of time to solution just essentially as the runtime divided by the probability of success. Okay, so time to solution as a function of log problem size. And this is for some, it doesn't matter what the details are, some hard spin glass problem whose ground state you're trying to find. And in this case, we're using simulated annealing, which is a well-known classical algorithm for these kind of problems. And two cases are being compared here. One is where you run simulated annealing with a fixed anneal time. It's really the number of sweeps in annealing, but it's the same as the anneal time. So let's say we fix the anneal time. We get the blue dots. Whereas if we optimize the number of sweeps or the anneal time, we get the red dots. And it makes sense, right? So if you don't optimize, you're going to get an artificially large time to solution. But you see what the problem is. The problem is that the scaling that you get in the unoptimized case is false, it's fake, and it's better than the true scaling, right? This flat scaling would seem to suggest that you can solve this problem with a good scaling better than the true scaling. So this is a very tempting trap to fall into, and I'll just say that many people have, and we're going to try to avoid this trap. So very important to optimize the anneal time in order to get an optimality certificate. Okay, so with that in mind, this talk will focus on results that we obtained with the D-Wave machine. So I want to give you a very quick history of D-Wave and USC. We established our first we established our quantum computing center focused on D-Wave in 2011 with the help of Lockheed Martin. And the first chip that was installed there was a 128-qubit chip, the D-Wave 1 Rainier. And that was followed by a series of upgrades up to 512 qubits. NASA, with the help of Google, were in the game as well a few months after we did this upgrade. And then we did the upgrade to the D-Wave 2X, 1152 qubits. The D-Wave 2000Q came later. We skipped that generation. And currently at USC, we have the Advantage 1 with almost 6,000 qubits. And this machine has been installed also in Jülich. And next year will be installed at Davison Tech, which is a company, I believe, in Alabama. Okay, so I should say, this is the last time I'll mention the physics of what is going on inside this chip. These are superconducting flux qubits, and of course, there's a whole long story as to whether these are high quality and so on, what their T1 and T2s are, and how they compare to transmons and all that. But let's just say that with the increase in these generations, the quality of these qubits has also remarkably increased as well. All right, so the other important thing to know about the D-Wave chips is the connectivity graph. So in all previous generations, up to but not including the current Advantage generation, the connectivity is this, what they call the chimera graph, which is a graph that has degree 6. So the blue circles here are the qubits, and the black lines are the couplings between the qubits. In the latest generation that employed chimera, that was the 2000Q, there were roughly 2,000 qubits and 6,000 couplers. In the current Advantage generation, the degree of the graph has increased to 15. It involves actually closer to 6,000 qubits and 35,000 couplers. So this is ultimately the type of architecture that I'll talk about where we have our newest results. I'll just flash this. Pretty soon, there will be a new architecture with degree 20 and more than 7,000 qubits called the Zephyr. All right. So the next thing I want to do is I'd like to give you a survey of the last 10 years or so of work on trying to demonstrate speedups in optimization using these devices. And so most of this work was done on the Chimera-style devices up until 2021, and as of 2022, we started to use, and others, the Pegasus graph. Okay, so let me rewind the clock 10 years now and tell you about one of the first results on trying to demonstrate speedups. So this was work that we did with the what was it? Now I forgot which machine it was, but I guess it was the D-Wave 2 at the time. Anyway, so the idea was, here's the Ising Hamiltonian. We generate 1,000 random Ising problem instances on the Chimera graph. And then each one of these instances, we ran 1,000 times. We knew ahead of time for the particular family of problem instances that I'll describe in a moment, what the solution was, what the exact ground state was, because we computed it using classical means on the side. So we knew the exact solution. So we were able to count the number of successes, and then we just defined the empirical success probability as the number of successes divided by 1,000 times, 1,000 run times, right? And then we repeat this for different problem sizes, n. Okay, so that's the strategy. And here are the results. And what you're looking at is the time to solution as a function of square root of the number of spins, square root for technical reasons that don't matter. We were using a fixed anneal time here, which is not an optimized anneal time. So remember what I said earlier about what happens when you don't optimize the anneal time. We didn't have a choice here but to use a fixed anneal time because we couldn't make the anneal time any shorter than 20 microseconds. And we always got our best results at 20 microseconds. So we knew that we were doing suboptimal annealing here. And the D-Wave results are the solid lines, and the dashed lines are simulated annealing. And what we found then for problems that involved 0 local fields, and the J's were chosen randomly as plus or minus 1, what we found was these results here for different quantiles of hardness. Right? So the median, well, that's the 50 percentile green lines here. The hardest problems were up here, and 99%. The easiest problems were the 1%. So we classified problems into how hard or easy they were, and what you were seeing is that, for example, for the median, it's very hard to distinguish D-Wave from simulated annealing in terms of the scaling behavior. For the harder problems, D-Wave is doing somewhat worse than simulated annealing, and for the easy problems, D-Wave seems to be doing better. But unfortunately, this scaling cannot be trusted for the reasons that I explained before, what happens when you get unoptimized anneal times. So this result from 2014, simulated annealing is not the best possible classical algorithm. We knew that as well. So we concluded that there was no strong evidence for a speed up here. If anything, probably evidence for a slowdown when you look at the harder instances. So why no evidence of a speed up? Well, of course, we know that the decoherence plays a role. These devices had a T1, T2 time of around 10 nanoseconds, but the anneals themselves last orders of magnitude longer. There are finite temperature issues, control noise. And also there's another, in a way, more interesting reason for why there was no speed up here, which is it turns out that this choice of problems that we only realized that later, these random Ising problems with a j of plus or minus 1, they were too easy for simulated annealing because you can actually prove that there's no spin glass transition in these problems for any finite temperature. The spin glass transition happens at t equals 0. So with that in mind, we went to harder problems. Okay, so a year later, we looked at what we call the frustrated loop problems with planted solutions. The idea of planting a solution is kind of nice. Planting a solution means you know what the solution is ahead of time, but you hide it in some kind of cryptographic sense. You're able to hide the solution from the device that is trying to solve it, even though the solution is actually known to you, the planter. So what are these frustrated loop problems? We randomly generate antiferromagnetic frustrated loops. So every one of these loops that you're seeing here is an antiferromagnetic frustrated loop. At least one of the spins is unsatisfied. And we make m of those over n qubits, and that gives you a clause density, alpha, the number of loops divided by the number of qubits. And then for these kind of problems, classically, then we add the Hamiltonian of all the loops, right? And then for these kind of problems, it's known classically that there is an easy, hard, easy transition as a function of the clause density. So you expect problems to be easy for small clause density, again, easy for a high clause density, but somewhere in the middle, there's a phase transition. And we were able to see that when we ran these experiments on the D-Wave 2 at the time. So here's the time to solution as a function of clause density, and as you increase the problem size, which is measured in terms of the number of chimera unit cells, you see this peak developing here, which is nice evidence for the emergence of this SAP phase transition as a function of clause density. Okay, so that confirmed that this machine was doing something sensible. But of course, what we're interested in is the speed-up question. So here is the time to solution for D-Wave with the different colors denoting the different clause densities over here versus different types of solvers. Now, it's not just simulated annealing, which you see has not great scaling. We also used other types of classical heuristics, simulated quantum annealing, which is a classical simulation of quantum annealing. Basically, quantum Monte Carlo, that's what this is. A spin vector Monte Carlo algorithm, which is a classical simulation of D-Wave specifically, where you replace each qubit essentially by a magnet with no entanglement. And this highly fine-tuned to the chimera graph algorithm due to Hamzy, Freitas, and Selby, which you can see scales the best. And if we take the ratio of these curves, so that's the speed up here is just the ratio of the time to solution of, let's say, HFS to D-Wave. So if this slope turns negative, then we have a D-Wave disadvantage. If it's positive, then we have a D-Wave advantage. And we see that benchmarked against HFS, there is a slowdown for essentially all clause densities. Okay, and again, unfortunately, in these cases, we were not able to optimize the anneal time yet. That's coming. So, unfortunately, still no evidence of a speed up. Okay, so up until now, no optimal anneal time. when there's no optimal anneal time that you can certify, all you can certify is really just a slowdown, but you can't claim that you have a speed up. We were well aware of this. We were searching for a long time for problems that do exhibit an optimal anneal time. And finally, we found such an example, and this involved combining the idea of frustrated loops with an idea from the Google team, which was called the tunneling gadget. So we combined these two things, and here's an example of a tunneling gadget. I won't explain exactly why it deserves the name tunneling, except the obvious explanation that you can demonstrate evidence of tunneling in this kind of a gadget. And what's the gadget? So this is a gadget of 8 spins. The local fields are denoted inside the circles. The blue lines are ferromagnetic +1 couplings, and the 2 dashed red lines are anti-ferromagnetic. The ferromagnetic are -1, and the anti-ferromagnetic are +1 couplings. So you take this gadget, and you place it at random in 10% of all the chimera unit cells. And this is like a cookbook recipe. It's hard to explain exactly why things work. So these are all nice heuristics. And you combine that with the frustrated loops that I talked about before. And lo and behold, we now are able to certify the existence of an optimal anneal time for a variety of different problem sizes. L is the number of unit cells in one dimension. So it's really an L by L chimera graph. And you can very clearly see here the time to solution as a function of the anneal time. You see the existence of a shallow but distinct minimum in the time to solution. So this was the first example of certifiable optimal anneal times, which allowed us to extract meaningful speed-up statements. So what happened when we benchmarked this now certifiably optimal scaling of D-wave versus simulated annealing? So first of all, time to solution, again, is a function of square root of the number of spins. And we're fitting to the larger problems to avoid some finite size scaling effects. And so this is simulated annealing. This is D-wave. And if you extract the slopes, lo and behold, the slope, which is now certifiably optimal for D-wave, 0.76, is smaller than the slope for simulated annealing. So we have a speed up. But the speed up is only versus simulated annealing. Right? And if you look at other algorithms, there is no speed up. Right? So in particular, focus just on the green curve. It's simulated quantum annealing again, or this quantum Monte Carlo algorithm. You see that now the slope is about half that of the D-wave slope. So while we had a speed up against simulated annealing, which is certifiable, there's no speed up in general. So we're still stuck. Okay. So next, I'm not going to go into detail. There's fine print here about how exactly these instances were constructed. We decided to look at so-called 3 regular, 3 XOR planted solutions. Again, the planting idea, but now for these NP-hard 3 regular, 3 XOR problems, which are known to have a golf course-like energy landscape. There exists an exponential number of local minima below a finite critical temperature. And heuristic algorithms are expected to scale exponentially in terms of finding the ground state on this golf course, right, with a single hole with lots of false minima, exponentially many. But these are planted problems, right? So we actually do know what the problem, what the answer is, what the ground state is, because we planted it. And here the results were really quite disastrous, I'm afraid to say, for D-wave. This is the time to solution as a function of problem size. Here's the D-wave scaling. The 3 latest points here are points with a certified optimal anneal time. So we can trust the scaling based on these 3 points. And then we're benchmarking here against a large number of really fine-tuned, highly capable classical heuristics for this kind of a problem. The classical winner is the so-called set on GPU from the Parisi group. massively parallelized, runs on GPUs, and very, very fine-tuned to this particular problem. And then there's a bunch of other methods. The slopes of the labels here are the slope of the set on GPU, and so you see that everything else has a steeper slope than the set on GPU. So, for example, the Fujitsu digital annealer, the Toshiba simulated bifurcation machine, MEM computing, and parallel tempering, and we'll come back to parallel tempering. This is parallel tempering without so-called isoenergetic cluster moves, which will play an important role in a bit. But the bottom line is, no matter what we benchmarked D-Wave against, it was doing far worse. And this was quite an exasperating situation at this point. So what to do? Well, we decided to try to go to a different paradigm. And the paradigm shift I already alluded to is a very simple one. Instead of trying to solve exact optimization problems, let's try to solve approximate optimization problems. And so that makes sense because exact optimization in some sense is a zero temperature limit. Of course, this is hardware that operates at finite temperature, and it's susceptible to, even at zero temperature, it would be susceptible to decoherence and to diabatic excitations and control errors, and finite temperature only makes things worse. So let's look at approximate optimization that is more tolerant. Okay, so we need a new metric. Here's the old metric. This was the metric that was appropriate for exact optimization. So the time to solution metric, right? And I emphasized that with the time to solution metric, we were looking for the probability of finding the exact ground state energy. So the metric that we can use to replace this one that works for approximate optimization is where we set some tolerance, I'm calling it epsilon, sometimes known as the optimality gap in the, what's it called? Well, there's extensive literature on classical optimization where this kind of a quantity appears. And so the optimality gap, or this tolerance epsilon, is simply a tolerance of being above the ground state energy by some fraction. Okay, and this works, this metric is appropriate when you have a non-zero, when you know that your ground state energy is non-zero and it's extensive. Right? Otherwise, if the ground state was allowed to be zero, then of course this wouldn't make sense. But we know for the problems that I'm going to talk about that E0 is both extensive and non-zero. So this becomes an appropriate metric. So this optimality gap, epsilon, is going to let us quantify how approximate our solutions are going to be. Okay. So can we demonstrate a quantum speedup using this metric for approximate optimization, where epsilon is strictly greater than zero? All right, so before I can show you these results about approximate optimization, I want to introduce an error correction technique, because we, of course, are well aware of the issues with noise and decoherence in these devices. And in fact, we developed an error correction method for quantum annealing more than a decade ago. And we've used it extensively, in particular also in the problems that I'm going to tell you about. So here is a quick description of this error correction idea. We're severely restricted in what we can do with quantum annealing devices, right? These are not gate model devices, so it's not like you can measure on an arbitrary basis and perform arbitrary gates. No, you can't. You're limited to running a transistor aliasing model, and you can only measure on the computational basis. So with that in mind, we can encode into a repetition code involving a lowercase n qubits and define an encoded Hamiltonian. So the bars are the encoded Pauli matrices. And these encoded or logical operators So the logical sigma z is just a sum over the individual sigma z's. And the logical zz is, as you can see in this little illustration here, if this is one logical qubit in red and another one in blue, then the logical sigma z is just the pairwise sum of the individual zz's. Okay, so this is actually just a simple repetition code with stabilizers, and you can add a penalty term, and this is inspired by work due to Steve Jordan, Farhi, and Shor from a long time ago as well, the idea of adding an energy penalty. So not only are we encoding into this repetition code, we can also add an energy penalty term, which is the sum of stabilizers of a bit flip code. Visualized here, so there's an extra penalty qubit that we add. So here are the 3 data qubits, and here's an extra penalty qubit. And we ferromagnetically couple the data qubits to this penalty qubit. And the idea is that, well, you can think about it in the Jordan-Farhi-Shor language, or you can think of it more intuitively as just enforcing agreement between these 3 data qubits to whatever the value of the penalty qubit is. Right? So this reduces the probability of independent bit flips. It increases the probability of collective bit flips depending on the value of this penalty qubit. But the point is, it reduces the probability of independent bit flips. Okay, so we have an encoding into a repetition code. We have this energy penalty term. Now we combine the two things. So we take the encoded Hamiltonian over capital N variables. Again, each one of these is really a lowercase n repetition code. We add the penalty Hamiltonian. There's a parameter here, gamma, that we're going to optimize the scale of the penalty. And that's a separate optimization problem that we have to perform. And then we take this encoded Ising plus penalty, and we add it back to the transist field, and we run the quantum annealing. Right? And now notice that the transist field I cannot encode because of restrictions imposed by the D-Wave devices. In particular, the logical X here is a tensor product of X's on all the qubits, and that's not an available interaction. Right? So the transist field is not encoded. What is encoded is only the problem Hamiltonian, and we add this penalty. Okay, so that is the idea. Then we decode at the end by a majority vote of each encoded qubit. So we just do a majority vote on sets of 3, let's say. And expect to get a better answer than if we didn't do this. Right? And we wrote a series of papers explaining exactly why this, what we call quantum annealing correction method, QAC, why it works. And you can read about the details in these papers, but the bottom line is that you can show that this reduces the effective noise strength by a factor of square root of little n. It reduces tunneling barriers, and it lowers the effective temperature. Right? So there's 3 good reasons here why this technique actually helps in quantum annealing. All right, so now back to implementing this in the context of the latest generation of the D-Wave devices. And so this is a zoom in on the Pegasus graph of the current D-Wave advantage that we have installed at USC. So here, the circles again are the qubits, and you see that we can actually group qubits as blown up here in exactly the same way that I just described. There's a penalty qubit, then a set of 3 data qubits representing a repetition code, ferromagnetic coupling between the penalty qubit and these data qubits, and so we can identify sets of 4 qubits throughout this Pegasus graph that let us do this encoding. All right, so we have logical qubits, and this shows each logical qubit now is a circle. Right? So we get an effective new graph that looks like this, where, again, every circle is an encoded qubit, and the couplings that are shown, there are 5 different types of couplings that you get as a result on this graph, which we call short and long diagonal, horizontal, vertical, and cluster. And if you zoom out even more, then this is the new induced logical graph. Again, every circle now is a logical qubit consisting of 4 physical qubits, 3 plus 1 in this manner. And this new logical graph, a subgraph of the full Pegasus graph, it's non-planar, which is good for hard optimization problems. It has a maximum degree of 5. Every logical qubit is coupled to up to 5 other logical qubits. And the largest size graph that we can embed, given the size of Pegasus itself, is 1,322 logical qubits, which is quite a bit and is enough to do interesting scaling experiments. All right, so this is the error correction strategy. This graph is the one on which we're going to run our approximate optimization problems in a moment. But before I talk about that, I also want to mention another type of simpler error correction strategy, a very, very primitive error correction strategy. No penalty, so forget the penalty for a moment. We simply embed 3 identical copies of this type of graph without using the penalty on the Pegasus graph, and we call that C3. So C3 is simply taking 3 identical copies of this subgraph, which you can of course fit in the Pegasus graph, and just taking the best of the 3 copies. Right? So we just run 3 copies in parallel. Whichever one gave the lowest energy, that's the one we use in each run. So that's C3, and that will play a role in what's coming. All right. So next, we need to find good problem instances, right? And so I told you about frustrated loops and 3 regular XOR set and so on. And so here we decided to look at a different set of problems, which were particularly well suited to this degree 5 graph. And these are so-called Sidon 28 spin glass instances due to Kotzgraber and company, and Humberto, my student, was co-author of this paper. So here the JIJs, the couplings between the spins are randomly sampled from this particular set of values. So the 28 is obvious, and the Sidon 28, this is somehow a well-known construction for number theorists. Has a nice property. It is that no sum of 5 numbers from this set equals 0. And that means that there can be no floppy so-called or 0 energy qubits. There's no qubit that experiences 0 local fields if you average over the J's that couple it to its neighbors. And that makes the problem classically harder. It reduces degeneracy if you have no spins that can just flop around at will. Okay, so this has a very low degeneracy. These are hard optimization problems. In fact, they're most likely NP-hard, given also the non-planarity of the graph that we're going to embed this on. So next, we need a classical algorithm that is really powerful. And the algorithm that we used here is not the set on GPU, because that was highly specialized to 3 regular XOR SAT, but rather the so-called parallel tempering ICM, PT-ICM, parallel tempering with isoenergetic cluster moves, developed again by Kotzgraber and company. And this algorithm, which I don't have time to explain, it's a hybrid of good old parallel tempering with an additional idea, the so-called isoenergetic cluster moves. Ask me about it if you're interested. There's a little cartoon here that explains how it works. But the bottom line is, what you need to know, this is as far as we know, the best classical algorithm for these types of problems in existence today. It has won all sorts of competitions. So we believe we're benchmarking against the best. But of course, we could be wrong about that. All right, so last thing I need to say before I can show you the results. Is that right? I don't want to lie. Yes. Okay. So the last thing I want to say is a new feature that D-Wave has enabled recently, which is called fast anneals. And this is available only with these new so-called advantage machines. So first, standard or slow anneals are anneals that take you down to half a microsecond. Remember that I said 20 microseconds early on? That was on the early generations of these D-Wave devices. With the latest generation, even the slow anneals are already somewhat fast. Oops, sorry. You can anneal as fast as half a microsecond. And what you're seeing here, the solid curves are the actual annealing schedules. The A and the B turns off the transist field, turns on the Ising term. But now there's also fast anneals. And the fast anneals are as fast as 5 nanoseconds, which is super interesting because the old T1s and T2s were 10 nanosecond, and they have now improved by a factor of 2 or 3. Okay, so we're well within the coherence time of these qubits now with these fast anneals. And indeed, there have been some really interesting papers from D-Wave recently, and I collaborated with them on the first one here, demonstrating what happens when you're in this coherent annealing regime, how you can do quantum simulation with very impressive results. I'm not going to talk about that. Please consult these papers. There's clear inklings of coherent behavior at a scale of thousands of qubits in these experiments. And when I say coherent, I mean essentially perfect agreement with the closed system Schrodinger equation for Kibble-Zurich type dynamics. So very interesting results. But we want to see if this makes a difference for approximate optimization. Okay, so unfortunately, because these annealing schedules, the fast annealing, the dotted ones, are different from the slow anneals, I'm going to report to you results where we had to separately optimize over fast anneals and slow anneals. We couldn't combine them in terms of finding the optimal anneal times. Okay. Oh, and yes, one other important comment. It's been known since the days of the first paper on adiabatic Grover that optimizing the annealing schedule is critical. Right? If you don't optimize the annealing schedule, you don't get the quadratic speedup in Grover. These schedules are not optimized in that sense. Okay, they are what they are. They were chosen due to hardware constraints, not in order to try to optimize scaling behavior. So there's an additional layer of optimization here which could be performed that hasn't been performed, and that is optimizing the schedule itself. All right. So with all that in mind, now I'm finally ready to show you the latest results reported in this paper and an update that will come soon. Okay, so I'm going to present a series of results to you for different values of the optimality gap, right? This tolerance that we're allowing for approximate optimization. Okay, so first, this bottom panel is the anneal time, the optimal anneal time, as a function of problem size. And remember, these are now logical qubits. So I'm talking about the Sidon 28 embedded on this induced logical graph that has degree 5, all right? And it has up to 1,300 plus logical qubits. So that's what this axis is. And wherever you see a solid circle, that means that is the optimal anneal time. All right? So we're able to certify optimal anneal times for these problems. So every point here corresponds to an optimal anneal time, except you see the green. I don't know if people in the back can see it. There are solid circles here on the green line, but not down here. And that's why this interpolation doesn't cover these other points. So we'll get back to that in a second. But wherever you see a line, that means it corresponds to certified optimal anneal time. So we're not fooling ourselves here with false scaling. All right, so now this is the time to epsilon as a function of problem size for different methods. First of all, the classical method. This is PT-ICM. Okay, and then there's quantum annealing correction, that's green. Quantum annealing fast, quantum annealing QAC-F, That is with the fast schedule. So QAC is with the standard slow schedule. QACF is with the fast schedule. And then remember the C3 method that I talked about, where we just take 3 classical copies, right? And without the penalty qubit. And we just take the best of the 3 copies. So we got a C3 and a C3F. C3, orange, and C3F is red. All right, so hopefully that's digestible. And what do we see? So for an optimality gap of 0.5%, which is a rather small optimality gap, right? So we're very close to actually still trying to solve the exact optimization problem. We see no evidence of a speed up. We see a slowdown. All right, so PT-ICM, the scaling is given here in these boxes. So that's the slope. Has a slope of 2.09. Here's the scaling formula. These, we're fitting to a polynomial. All right, so all of these problems can be well fit to polynomial scaling. Why? You might ask, didn't you say this was exponentially hard? Yes, the ground state, finding the exact ground state is exponentially hard. But we're doing the approximate optimization, okay? And that is not exponentially hard, as it turns out, at least not for these problem sizes. Okay, so slope for PT-ICM, 2.09. All the quantum variants have a worse slope. Before I go on, I want to briefly comment on this kink that you see here in the C3F, which corresponds to the kink you see here. So C3F, again, that is this 3 classical copies with the fast annealing schedule. The fast annealing seems to transition from coherent dynamics, which is down here, to incoherent dynamics, which is up here. So this transition, this kink, we know that we can explain it. I won't get into it. It actually corresponds to a transition from coherent to incoherent dynamics. And that is noticeable in the slope. And it's curious that the slope for the incoherent dynamics is actually better than the slope for coherent dynamics. All right, so now what happens if we go to a more relaxed optimality gap, so 1% as opposed to 0.5%, and things are looking a little better. The PT-ICM slope is 1.95. The best of the annealing results is now a slope of 1.68, right? So all of a sudden, we now have a speed up. It is a speed up that, in terms of error bars, this is 2 sigma error bars here, right? So we're 2 sigma each side. So we're with 1 sigma, we clearly have a certifiable speed up. With 2 sigma, not quite. Okay, let's make the optimality gap even larger, 1.25. So you see, one thing that's happening is that the QAC results become less and less certifiably optimal. We're left with shorter and shorter lines here, where fewer and fewer certifiably optimal anneal times for QAC, which is the green data. Now, what about speed up? So 1.89 versus 1.16 for QAC, and 1.76 for the C3 strategy. So that means we now have a speed up, again, up to 2 sigma error bars. We have a speed up for not just for the QAC strategy, but also for the simpler C3 strategy. And then finally, with an optimality gap of 2%, there are no more certifiably optimal anneal times for QAC, so that's why you don't see a green interpolation anymore. But the C3 strategy, which is the 1.41 here, is now even with 2 sigma, the 1.08. The 1.08, even with 2 sigma, is much better than the scaling of PT-ICM. And interestingly, also the QAC fast, right? So the error correction with the fast anneal schedule is now also certifiably better than the scaling of PT-ICM. So the message here is that as you relax the optimality criterion, you allow for more and more approximate solutions, you start to see a speed up. Right? And we can quantify it by looking, instead of at these curves, let's just look at the scaling exponent itself. So here, this axis, this polynomial scaling, is the S parameter that I was talking about. So this is S as a function of optimality gap value for the median instances. All these plots that I just showed you were the median instances, by the way. So here is the scaling exponent, first for PT-ICM, that's the purple. Or is it blue? I can't tell. I think it's supposed to be blue. And then QAC, green, C3, orange, and actually purple, QACF. And so where the QAC curve crosses the PT-ICM curve, well, to the left of that, we have a slowdown, but to the right of that, we have a speed up. Right? And again, it's a certifiable speed up with certifiable optimal anneal times. And the crossing happens for these other, the C3 and the QACF strategies as well, later. All right, so this is the highlight of the results. Demonstration of a quantum speed up using these D-wave devices for approximate optimization versus PT-ICM. Is there a better method? Possibly. I'd like to hear if anybody knows of something else we should try. I said this was for the median instances. If you look at the easier 25th quantile, 25th quantile, or harder 75th quantile, the results are basically the same. The crossing point changes a little bit, but apart from that, it's the same. So this is also robust to problem hardness, this result. Okay, so let me conclude. I think we found, I don't know if it's the sweet spot, but it is certainly a sweet spot for quantum advantage in optimization using analog quantum hardware. We demonstrated this speed up in approximate optimization using quantum annealing. It happens roughly at an optimality gap of 1% versus PT-ICM. We saw that errors and error correction, unsurprisingly, they matter. Error correction helps. The fast annealing has been a little bit of a disappointment here. The fast annealing gives us access to this regime of coherent dynamics, which was demonstrated separately by the D-wave guys. We don't really see evidence that it helps all that much. I mean, here again is the QACF result. You do get a speed up, but it's not better currently than doing the standard slower anneals. The big caveat here, of course, is that the holy grail is exact optimization and small epsilon approximate optimization, and those remain hard for quantum annealing. We don't see an advantage there yet. But then we haven't optimized over everything yet. So in the future, as I alluded to, we'd like to benchmark against even better solvers than PT-ICM, if they exist. And now that we have this baseline demonstration for the Sidon 28 instances, which of course are not practically interesting in any meaningful way that I can think of, it would be nice to find problems that are more practically relevant. And finally, it's curious that we weren't able to exploit fast coherent annealing yet, and so the next step there is to try to optimize the annealing schedule itself, possibly in collaboration with the hardware folks at D-Wave to see if that is the issue, and maybe we can push coherent annealing into a regime where it also exhibits a more convincing speedup. With that, thank you.
We only have time for one question.
So, quite a saga and very impressive results. When I look at these very impressive results, I wonder, is there a sense about thinking about the energy spent in terms of that metric? Because you're comparing to things that run on as hardware that we don't know, what the kind of energies are being spent. So, is this something sensible to think about in terms of energy budget?
Absolutely. So, DARPA is very interested in those kind of questions. I've been on a couple of DARPA programs, quantum annealing programs, where that was one of the questions that they encourage us to look into. Energy spent is, in some sense, kind of trivial for these problems because the energy you spend running in quantum annealing is just the energy at this scale that it takes you to keep a dilution refrigerator operating. So in some sense, it's just a fixed cost.
Right.
Of course, that's not the case for running these classical calculations, which scale terribly. You can consume a ton of power, and we also know that from quantum supremacy results and the work that Google and others have done in that domain. But yeah, I think it is an interesting question, and it might be another way to try to quantify quantum advantage, and it's quite likely promising.
Yeah, I mean, in terms of a quantum advantage, that seems to me the metric to assess advantage.
It's a metric, right? It's so typically, as somebody who's worked in quantum computing for a long time, the energy question came up much later. And in the beginning, we were always concerned with time, and more precisely scaling of time. But time and energy are closely correlated in this context.
Right.
Yeah.
And unfortunately, we are also short on time. And next speaker will be Yuan Liu. Yeah, let's thank Daniel for the nice talk.